In section 9.3, we're going to study three-dimensional coordinate graphing. When we graphed in 2 dimensions, that means on the regular xy coordinate plane, we would graph ordered pairs, and there would be 4 quadrants. In the 3-dimensional coordinate plane, there are now 3 axes, and the 3 axes are x, y, and z. Instead of having ordered pairs, we have these things called ordered triples because we're working in x, y, and z. And instead of having 4 quadrants, we have 8 octants. Graphing in 3 dimensions is kind of hard, so I give you this picture to show you what's going on. However, I will not test you on it. If you want to plot a point x, y, z on the 3-dimensional coordinate plane, you would do like you do with a 2-dimensional coordinate plane. You would start at the origin. And first you'd go along the x-axis, however many spaces. To go along the y-axis, though, you would figure out how many spaces you're going to go and think about a line through that point on the y-axis, but parallel to the x-axis. And that's how you would determine how far you would go to the left or right. Then you're going to go up or down depending on if z is positive or negative. Notice the box on the 3-dimensional coordinate plane. What we end up doing is we end up drawing this box. This is wherever z is, we would start here and draw ourselves a box. So we would go in the x direction, the y direction, the z direction, stop, and that's where point x, y, z is. So now if I take this all the way, and I attempt to do this with the point 2, 4, 7, what we would do is we would start on the x-axis and we would go 2 units along the positive x-axis. The negative x-axis is behind us. This is where the negative x-axis is. Then I would go 4 units to the right. 1, 2, 3, 4. And I would think about a line through that point on the y-axis, but parallel to the x-axis. And this is how far I'd go. And then I'm going to make the bottom of this rectangular prism. The next thing that I would do is I would go up 7 units on the z-axis. 1, 2, 3, 4, 5, 6, 7. We'll say 7's up here. And I would start here, and I would start creating a box. Let's see, I went too far. Here's my 3-dimensional box. Now, to find the point 2, 4, 7, 2 along the x-axis, 4 along the y-axis, 7 along the z-axis, and this is where the point 2, 4, 7 would be located. In 2-dimensional geometry, the graph of an equation involving x and y is a curve in a plane. So if you draw a coordinate plane here, we draw quadratics or linear equations, cubic equations. In 3-dimensional geometry, however, when you graph an x, y, and z, instead it represents the surface in space, like a plane. And in geometry, we learned about this thing called a plane. It kind of looks like a sheet of paper floating in space. So we're going to describe the surfaces represented by each of the following equations graphed in 3 dimensions. The graph of z equals 3 is not going to be a line through the z-axis. Like if you think about the graph of x equals 2 in 2 dimensions, this is what the graph of x equals 2 looks like in 2 dimensions. Instead, we're going to graph this in 3 dimensions, and it would look something like this. Here's your x, y, z coordinate plane. Here's where z equals 3 is. There would be some space through it that is parallel to the xy coordinate plane. So the surface of z equals 3 is a space that is parallel, I should say it's a plane that is parallel to the xy plane. For y equals 5, here's my 3-dimensional coordinate plane. Let's say y equals 5 is here. It would be some plane parallel to the xz coordinate plane. So it would look something probably like this. And I don't know how big the space is, but that's what it would look like. So it's a plane parallel to the XZ plane. Now let's go to the stuff that is important to us. Finding the distance between 2 points on the three-dimensional coordinate plane. This formula looks awfully similar to the distance formula in 2 dimensions. Here is the distance formula in 2 dimensions. All I tacked on was a z. Oops. So now, in order to find the equation of a sphere, oops, I went too far. Here we go. In order to find the distance between the points 2, -1, 7, and 1, -3, 5, I would do 1 minus 2 squared plus -3 minus -1 squared plus 5 minus 7 squared, and square root that answer. So -1 squared plus -2 squared plus -2 squared is 1 plus 4 plus 4, which is going to give me 9, and the square root of 9 is 3. So it turns out that those 2 points on the three-dimensional coordinate plane are just 3 units apart. In 2 dimensions, we talked about circles, and the equation of a circle was x minus h squared plus y minus k squared equals r squared. So in 3 dimensions, instead of a circle, we have a sphere. So the center of a sphere, we're going to say, is HKL, which means we need to tack on a z minus L squared into the equation. So to find the equation of a sphere with a radius of 5 and a center of -2, 1, 3, all I'm going to do is plug this in for h, this in for k, this in for L, this in for r, and then I'll be done. Watch your negatives. The first binomial is going to be h, or x plus h squared, oops, which is 2 actually, plus y minus 1 squared plus z minus 3 squared equals 25. And that's the equation of the sphere. When we talked about circles, we also talked about something called general form. General form's not useful because I don't know where the center and the radius are. So we have a process for changing this to standard form. It was called completing the square. We put the x's together with a blank. We put the y's together with a blank. We put the z's together with a blank. Oops. And then we moved our constant to the other side. And since we're going to add 3 new numbers to the left side of this equation, we're going to add 3 numbers to the right side. Remember that the way you figure out how to complete the square is you take the middle number, divide it by 2, and square it. So 4 divided by 2 is 2, 2 squared is 4. 6 divided by 2 is 3, 3 squared is 9. And 2 divided by 2 is 1, 1 squared is 1. Once we've created those perfect square trinomials, they factor really easily. So the first trinomial factors into x plus 2 squared plus y minus 3 squared plus z plus 1 squared is equal to 9. Or 8. Sorry. And that would be the equation of the sphere in standard form. The center would be at -2, 3, -1. And since the radius is 8, the radius is going to be the square root of 8, which is 2 square root of 2. The intersection of a sphere with a plane is called a trace of a sphere. If you think of a plane like a sheet of paper, and you were able to put that sheet of paper through a ball, the trace, the part of the paper that's inside the ball, would actually create a circle. So let's talk about the trace of this sphere, x minus 2 squared plus y minus 4 squared plus z minus 5 squared equals 36. In the xy plane, if I want to stick this through a ball, the z component would be 0. So what I'm going to do is, in the equation of the sphere, I'm going to rewrite this having plugged in 0 in place of z. This, 0 minus 5 is negative 5, negative 5 squared is 25, and then you subtract 25 from over here, and you get 11. So you'd get x minus 2 squared plus y minus 4 squared equals 11. And that's the remaining circle. The center is still at 2, 4, 0, and the radius is going to be the square root of 11. But in part B, instead of giving me a plane, they give me z equals 9. Remember, z equals 9, if you come all the way back here, we did z equals 3, and it was a plane that was parallel to x and y. So all I'm going to do is I'm going to replace the z with a 9. So x minus 2 squared plus y minus 4 squared plus 9 minus 5 squared equals 36. I'm going to simplify this. 9 minus 5 is 4. 4 squared is 16. I'm going to subtract 16 over here. And I get x minus 2 squared plus y minus 4 squared is equal to 20. So the center this time is at 2, 4, 9, and the radius is the square root of 20, which is 2 the square root of 5. And that is section 9.3 on three-dimensional coordinate geometry.